Okay, so the next paper is called Monolith, Circuit-Friendly Hash Functions with New Nonlinear Layers for Fast and Constant Time Implementations. And Marcus will give the talk.
Yeah, so thank you for the introduction. So then, together with Lorenzo, Dmitry, Reinhard, Christian, and Roman, some of those are actually here. And it will be about yet another circuit-friendly hash function called Monolith. Yeah, first some outline though. So why do we need circuit-friendly hashing? I will try to make this part very slow because we have heard in previous talks already some of the motivation. Then I will talk also to a specification, to the security and the performance analysis, of course. And at the end, I will try to close the talk with some future work, which will include the usual stuff, like always more analysis is good, right? And I will also talk about an interesting problem. It's not necessarily related to symmetric crypto, but I figured it's still maybe worthwhile to present it briefly. All right, so let's start. Why do we need those hash functions? Well, in these zero-knowledge use cases, there are many settings where we need them, and they're not always circuit-friendly. So sometimes they're used just for FHE or something like that. But in many cases, they're actually circuit-friendly or have to be circuit-friendly for performance. And one of those cases is the Merkle tree membership proof, where we just like create a Merkle tree, for example, and then we want to prove in a somewhat efficient method that we have some element or some leaf in this Merkle tree. It's also used for commitments in this case here. All right, so there are some alternatives out there. So for example, Poseidon, Rescue, and I was about to say they're only a few years old, but actually Poseidon and I think also Rescue are 6 years old already. And they're better than SHA-3 in these ZK circuits, although this seems to shift a bit because some of the newer techniques allows one to actually be quite efficient also with classical hash functions. But still, they're still better. But they're much slower in native hashing. And this is a problem because if you want to do a Merkle tree proof, for example, you first need to compute the actual tree. And this costs a lot of time, as we will also see. And the second motivation of this paper was that many of the newer use cases or prime field use cases in proving system focus on small primes. And the reason is that they are not always depending on elliptic curve pairings, so more like on the code-based assumptions. And there we can actually use small primes. So for example, 64 bits or 32-bit primes. So there are some alternatives already, which are similar to Monolith, like for example, reinforced concrete, but they only work over larger prime fields, which is not the case here. So yeah, what's that about the native hashing performance? So hashing is often a bottleneck, and on the right side, we see some rundown here of a proof, actually. Don't ask me which one, I don't remember anymore. But we can see in the screen part, which is rather big, this is only for hashing, so only for Merkle tree hashing. And I would of the entire proof then, specifically if we already accelerate, for example, the orange part, the NTT part. So it's quite important to make hashing fast because then the proof also gets much faster. So the question is, of course, how do we make it fast by also retaining some level of security? Yeah, recall we're working with small primes, so we focus only on those. And we know that, I mean, this is true for the native performance, but it's also true for the proving systems, that if we have like components of high degrees, like x to the power of 2 to the power of 50 or something, then this is quite slow. We need a lot of multiplications in the native implementation, but we also have the problem in the circuit that we have to prove this, and this is quite expensive. So in the past, we tried to focus more on these low degree components, like for example, x to the power of 3 or x to the power of 5. But it turns out it's like not so good as well, because like you also pay for the circuit. This is fine, but you need to do the reductions and the multiplications and so on. And this is not so good. And this also includes the linear layer, because of course you only have constant multiplications, but you still need to do reductions. And this becomes very bad if the prime field is large, but also in the 64-bit case already, it's not very good. So the question we asked ourselves was, how can we do less than one CPU operation per state element? And of course, this is not possible for the entire permutation, at least not if we consider security and not any like specific instructions. But the hope was that maybe this is possible for some parts of the permutation. And this is also the main point of monolith, actually. So this is one way of making it faster. And the second ingredient we need for this is something which is called the lookup argument in these ZK protocols. I will, on the next slide, very briefly talk about this and how the lookup argument actually works or what it does. So this will also help us to achieve this goal. And yeah, finally, we can use some vector arithmetic also, which is nice. Okay, so this lookup argument, or at least modern lookup arguments in ZK protocols, allow a prover to prove an arbitrary relation. So this is true, of course, only to some extent. And this extent or this limit is mainly the input size. So we have some input size limit. For example, we can prove relations of 16 bits of entropy, so 2 to the 16, if they're invertible, right? And this is good because it means that we can essentially mimic a function, an algebraic function, which has degree like approximately 2 to the 16, which would otherwise not really be possible if we just use a simple degree 2 to the 16 function. It would be very expensive. But with it, we can make it in, well, somewhat efficient way. And yeah, so the question was, how can we actually use this in a prime field? Because we have a 64-bit prime field, we have a 32-bit prime field. But now we have a proper 16-bit functions with 2 to the 16 inputs. So how can we use this? And the main idea is essentially to split the prime field element and then to apply this function to the individual limbs of the original input. I will also talk about this in a minute. So yeah, so what are the main properties of this permutation? So first we have quite a good native performance, I'd like to say. It's implementable also without lookup tables in software. So which means you do use the lookup argument or the lookup technique in the proving system, but you do not use memory lookups or cache lookups in software. So you are also arguably resistant against at least this type of side channel attacks. Yeah, and finally, it focuses on this FHE-based proof systems. So FHE-based proof systems are essentially proof systems which get their security guarantees from codes, so from Reed-Solomon codes in particular here, and they allow one to use, like, to arbitrarily use some prime number or to choose it. And these prime numbers here are quite popular in the nowadays, but they're effectively chosen to be very efficient for arithmetic. So you see some generalized Mersenne prime numbers and also a proper Mersenne prime number here. And these are actually the setting also we consider for the permutation. So yeah, what does it look like then? So here we have a single round function. We have at least 8 state elements, and we have, for each round, we have these 3 layers. So the first layer is maybe the most novel one here. So I will talk about this later. And then in the second and the third layer, we have something like a Feistel, a quadratic Feistel. And in the last layer, we essentially have just a matrix multiplication. So we want this matrix to be MDS, but it's just a matrix multiplication. Okay, so let's first talk about this Feistel layer. It's called bricks in our design, and it's constructed from this Feistel layer construction here, and it's quite efficient in plane, of course, because degree 2 is quite fast. It's just 1 multiplication, and then you have like t-1 multiplications for a t-word state. And yeah, this is good in plane, but it's also not too bad in the proving system because there's a single degree with the single constraint, sorry, with degree 2, and this is quite nice. So it's good for the proving system. And the thing is that all of that works natively over the prime field. So there's no magic involved. It's just like prime field multiplications and additions. And yeah, about the statistical properties, I will talk about this very quickly also later. But of course, the lower degree, the better in general, because if we build the difference polynomial, there are not many roots we can find for the solution. So it's quite good. And yeah, then the concrete layer, which is, I will not talk about this a lot. It's a normal matrix multiplication. Essentially, we want for like a fast multiplication. We just use 2 entities. We just mimic a polynomial multiplication effectively. And this works with any circulant matrix. Doesn't have to be MDS, but in this case, it also works. Okay, so let me come to this sparse layer then, which is probably the more interesting one. So like the previous layers, like the bricks layer and the concrete layer, just normal prime field arithmetic, but this is different here. So this layer is actually over F2, we can say. And the idea is that every state element gets first split into a number of limbs. So this depends on the instance. But for example, we can split a 64-bit element into 4 16-bit limbs. And the idea is to do that and then to apply some lookups to the individual limbs. And so these limbs can be 8 bits or 16 bits large. 16 bits is mostly better in many settings in the industry, actually. And then the idea is to apply this SHA-3-like SBox to each of those limbs. And what is nice about that first in the proving system, we can just use this lookup argument. It's either an 8-bit or a 16-bit lookup. This is quite fine. But also in plain, it's very efficient because first we don't need to use memory lookups, and we can just compute many of those SBoxes in parallel using a vectorized implementation. And this is available on most modern CPUs, and it's very fast actually. It's actually the fastest of the 3 layers here in each round, but in a proving system, it's the slowest and most expensive. I will also talk about that towards the end. Okay, so very quickly about the security then. We have, of course, like all statistical and algebraic security. Statistical one is mostly fine. So it comes from bricks and concrete. It's like the argument is based on this quadratic SBox in the Feistel. But the bars is weaker. And there actually has been a paper very recently where we use a similar SBox in a newer design. And there has been a paper very recently which actually shows that the weak differential properties of bars can lead to some attacks on reduced round versions. And reduced round means only one less round. Okay, so that's about the statistical security. About the algebraic one, because this is always something which is interesting in those arithmetization-oriented or circuit-friendly schemes. So this comes mainly from this bars component, which essentially like mixes the finite field with with a smaller field, the operations. So intuitively, and we also did many tests, of course. I would say that our security margin is quite big here. But of course, more analysis in the future will also be nice here. And I would also say that this is not completely novel. This has already been used in other constructions, for example, in this mod 2.3 constructions, which, from a couple of years ago. Okay, and that already brings me to some performance numbers. We always like to see performance numbers here. And this is actually new. This is something which at least one part here hasn't been included in the paper. We have CPU performance and hardware performance here. In the first part, CPU, so this was our goal, right? We wanted to be fast on CPU. And we have 2 settings. We have the 64-bit primes and the 31-bit primes. And we see that Monolith is quite fast compared to Poseidon 2, which is arguably like the most used circuit-friendly hash functions nowadays in these use cases. And it's quite fast, specifically if we focus on smaller state sizes. So smaller state sizes means if we, for example, if you use the permutation in compression mode rather than sponge mode, and if we have a larger prime, like the 64-bit one, because then we only need 8 elements in the state. If we move to larger state sizes, we see that, it's still faster, but the difference becomes smaller. And the reason for that is mainly because this linear layer is quite expensive, and the dimension, of course, increases of the linear layer if we increase the state size. But this is also the case in many other symmetric constructions, not here only. So this is nice, but what we wanted to show mainly is that we can actually reach SHA-3 performance. And in some cases, we're even faster natively than SHA-3. Of course, there are other options like Blake and so on. We cannot reach those. But so the purpose was to show that we can actually be in the same ballpark performance-wise as classical hash functions, while also being much more circuit-friendly. So this was the main goal of the paper. So this is about CPU performance on modern CPUs. We can then move also to hardware performance. So this is actually a custom hardware chip. We also tested it on that, and it provides a speed up of around 400 compared to the CPU performance here. This is cool, of course. It's actually not very good because the implementation has an IPC of, I think, 0.2 or 0.3, which is not really high. And for Poseidon 2 on hardware, we reach almost 1, so it's very unoptimized still, but it's quite fast. I guess we can make it like 3 or 4 times faster with hand scheduling, but still. But the main purpose of this part is that we also have SHA-3, and we see that there's a huge difference between Monolith, Poseidon, and SHA-3 on hardware. So this shows that in the future, maybe we can think about something which is circuit friendly, but also hardware friendly, not only software friendly. So because there's still a very huge gap there. Okay, so I promised some future work, and I will talk about that very quickly. So of course, it's always nice to have more security analysis, especially this interplay between like the prime field operations and this limb splitting and the F2 functions. Because yeah, like I said, intuitively, I think we have quite good security margin here, but we don't know with absolute certainty. So I think that much more analysis on this part would be quite interesting also for other constructions. Yeah, that's about security, and but similarly for performance, we always hope for more optimized implementations. I think that has been the case also for other symmetric primitives. They have been proposed and then they become faster over time, and so they tend to age like fine wine, at least if they're not broken. So there's still something to do here. And also on the hardware side, like I've said before, there's really nothing we have done yet here. Okay, so this is the usual stuff for future work, but I also wanted to briefly talk about another aspect of this work. It's not necessarily related to symmetric crypto, but maybe it's interesting. So why are those lookups actually so not so good in the proof? Why are they actually bad? And well, the reason is if you think about those lookups, well, usually those proofs work by applying something on a witness table. And every intermediate element, like the input state, the output state, but also intermediate states, they're included as witnesses in this witness table. And usually every witness takes an entire finite field element. So for example, an entire 64-bit field element. And if we do this limb splitting, of course, we have to include the input, the original input, but we also have to include each of the individual limbs, which means that we have, for example, if we split a 64-bit field element in 16-bit limbs, it means that we have 5 different witnesses just for that, which is a times 5 increase here, which is really bad. And the same for the output. We have y and then y0 to y3. So this is not so good because in many of those proofs, and specifically in these proofs which use these Reed-Solomon assumptions or codes, we need entities for the commitments. And actually we need 2 entities. One of those is even over a larger domain. And which means that those are very expensive in the proof. So if we increase the witness size, then question, can we somehow find algebraically, or can we find an approach where we can algebraically store many of those smaller limbs in a single field element and then access them efficiently? Because of course, if we just add them up, we already did this, but we also need to be able to access them in some low degree way. And there are some approaches using, for example, Frobenius automorphisms, and there are also some approaches known for binary extension fields using tower fields. And this is quite good because you actually pay what you commit to. You don't always pay a full field element, even if you commit only to 16 bits. But it doesn't yet work in prime fields. Or at least I don't know how it could work in prime fields. So if you want to know more about that, feel free to ask me later. We can also talk about that. And yeah, thank you for the attention.
Are there any questions?
Yeah. Thanks for the talk. So what operations make it not hardware friendly? Is it the squaring in the finite field?
Yeah, it's mainly the squaring. So I forgot to say it. For the bars layer, we actually on this custom chip, we have an instruction which does the entire bars layer in one cycle. So this is really good. What is bad is the squaring, but also the matrix is not really good.
Okay.
Yeah.
Thank you.
Sorry, I didn't get what was the criteria for selecting the S-box? Like why this S-box in particular?
Mm-hmm. Yeah, so this could also be done with an SPN, and it wouldn't be much worse, arguably. So the criteria was mainly performance on the protocol side, actually, because the bars. Yeah. We wanted to this one, right? Yeah, we wanted to keep it simple. We wanted to use something which is already known, and we could do anything for the protocol side. We could use any function which works over 8 or 16 bits, so this is fine. But we wanted to use something which is also efficient to implement in a vectorized implementation. So this was mainly the reason here.
Just a last question.
Thanks. I was wondering about this limb decomposition because your prime is slightly smaller than 2 to the 32 or 2 to the 64, so you don't have exactly 4 full or 8 full words. So how do you deal with it in the SBox?
That's a really good question. Yeah, so the SBox is still composed by 4 16-bit elements or 4 8-bit elements or something like that. But we do need actually an additional technique in the proof. So we need to prove that the input element is actually a canonical field element. Because otherwise we could apply any SBoxes and we mimic a permutation which is that. There's just one constraint, and I think it's even linear or quadratic.
Okay, then we can thank Marcus again.